I'm going to talk a little bit about kind of a cool aspect of friction. If you have ever seen a thing called Chinese handcuffs, it's this woven straw thing. It looks like this, and it's woven kind of diagonally, circularly. So you stick your fingers in, and then when you pull, it tightens, and it's hard to get your fingers out. So it's like this. When you put your fingers in, when you pull, there's a little friction in there, and it stretches it out because it's really easy to expand it like that. And when you stretch it, it becomes narrower. And when it becomes narrower, the normal force on your finger, the surface on your finger, becomes bigger. So the mu doesn't change between skin and this, I don't know, bamboo or straw or whatever it is. There's a certain mu that doesn't change. But when the normal force gets bigger, the force of friction gets much bigger. And the more you pull, the tighter it gets, the more the normal force goes up, so you can't get your fingers out. And I broke my wrist playing basketball in grad school, and they broke it really badly. And they wheeled in this thing. I had just bone on bone, and I still have this bump here. It was just bone on bone rubbing against each other. And they wheeled in this thing that looked like hangman, and it was this metal thing with these wire things hanging down like that, one for each finger, and it was just this wire. Oh my God. And they rolled that thing in and put my fingers in it and a thumb, and they put my fingers in it and they hung a weight down on it. And what it did is it took the bones that were rubbing together and stretched them out a little bit so they weren't rubbing. And it was blissful. It was wonderful. It's based on the Chinese finger trap. So when they pulled, the fingers, it still yanked up on the fingers, pulled down. I thought I was going to cry, but it was delightful. It felt so good because it's the one time all day where I wasn't in intense pain, so they could set the bone. Of course, there's a lot of problems setting the bone. Long story, they had to set it 3 times that night. 2 weeks later, they had to re-break it and reset it, and I had my arm cast like this for 2 months. Okay, but this business of changing the normal force and getting a bigger force of friction, there's a really cool demonstration we have with that. If you have 2 pieces of paper like this, I've got just like a catalog, it's like a magazine, it's the same material, glossy. There's almost no friction. It just glides. Something that's really small friction. Well, okay, and that's because force of friction equals mu times the normal force. The page doesn't weigh much, and mu is not very big because it's slippery stuff. Well, what if I put another, no, that's not going to work. If I put another sheet down there, right, now there are 2 surfaces. So it's 2 times mu. Oh, and the normal force is probably a little bigger because they're both weighing down. So let's say the normal force is twice as big. So just putting those in, you got 4 mu times, let's just say the normal force, the weight in this case of 1 page. Okay, so it's 4 times as big. And if I put another surface in there, 1, 2, 3, and maybe a little more, so it doesn't go up. It doesn't keep going exponentially like that, but it gets bigger and bigger. But even more than that, if you put a whole bunch of them together, if you just weave these things together, so you start with one and you get another catalog and put that in there, and then put another one in there, and then put another one in there, and so you get these 2 catalogs. They don't even have to be that many. I've got it up there with I think 150 pages. I'll show you. And what happens is not only are you getting more surfaces where there's friction, and not only is there a little bit of normal force, we're going to do it vertically, so the normal force is almost irrelevant from weight. But if you look at the top one, this one's pulling down, right? When you pull, that pulls down a little bit, and that actually, so part of that force that you pull with would be pulling down and compressing it. And it ends up being a kind of a big effect to the point where you get these 2 slippery catalogs and you interweave them, and it's almost impossible to pull them apart to the point where, and I've got to figure out how I can get this shown. Well, first of all, if you look up here, and I need to see where I'm going, I don't know if I can see it, but you can see I've got 2 sets of catalogs interwoven, and I've got those clamps. The clamps aren't holding them together. The clamps are just so I can connect it to the top surface there, And so I can get a grip on it. In fact, I'm going to move it this way so I can see while I'm doing this. So even though this is just two catalogs, slippery paper put together, now see, I'm pulling kind of hard and it's not coming. And so even with a whole body pulling on that, this whole contraption, this whole connection of paper, I can't see what I'm filming here. That whole contraption there, which is just two catalogs, nothing else, interwoven, is strong enough to hold up an entire human body. And I was jerking on it. My whole weight was on there, and I was jerking on it. So that's the power of that normal force. Of you have small mu, really small mu because they're slippery, a bunch of surfaces, so maybe times 150, but that's not that much because it's so tiny to start with. And then when they pull apart, they force the surfaces together, increasing the normal force. So kind of a cool friction demonstration.